welcome back to Physics in Action. I'm your host, Miss Nielsen, and today we are moving on. That's right, folks, we are heading back to basics today to start our discussion on motion. This unit 3, is all about constant velocity, where we will be discovering ways to describe things that are moving at a constant rate. More details to come. Today we're going to start in the field, where I have a very exciting report for you regarding intro to our motion vocabulary terms. And I've got a very special friend that I've recruited to help us understand those terms. Then we're going to head over to Studio 328, where Mr. Willauer will finish out our vocab set in helping us understand the difference between speed and velocity. Let's head over to the field.
So what we've got today are some very important definitions that will carry us through the rest of the year. So we're going to be talking about some definitions related to constant velocity today. So a couple of those definitions are really broad, but we will be applying them later on this year. So our first two definitions are scalar and vector. And these are like umbrella definitions. They cover many different terms, but it's important we understand their difference because like I said, we'll be using them throughout the year. So starting with a scalar can be defined as a quantity that's described by only magnitude. So that kind of seems loaded. Let's unpack that. By magnitude, I mean the number. It has a number. So a scalar is a quantity that's described by a number, which seems like pretty basic, right? But a scalar is pretty much just a number. So an example of a scalar is like saying you got 2.5 inches of rainfall. There's that number, 2.5 inches. So that's what a scalar is. It's just a quantity that has a number. A vector is a little bit different. A vector is a quantity that's described by magnitude and direction. So once again, we have that magnitude term, which means the number. So a vector is a number, but it also has a direction. So what does that mean? Well, it means that it's a vector, it's a number that's either pointing up or down, or left or right, or north and south, like actual directions. And to kind of better illustrate this idea of a vector that has magnitude or a number and direction, I've got a short little video for us that you might remember.
Hey. I'm applying for a new villain loan. Go by the name of Vector.
Vector.
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
There it is.
Vector!
Vector!
Because I'm committing crimes with both direction and magnitude. Oh yeah!
Oh yeah. So that's a vector. It's got a quantity that has a magnitude and a direction. So there I've got an arrow drawn that has magnitude and direction. But an example of this is if you were driving 20 miles per hour south. So we have that number there like we did up above with 2.5 inches. We've got 20 miles per hour, but the key here is that we have a direction. You are driving south. So that's a vector. So scalars and vectors are going to be really important for us as we move forward to understand what types of things are scalars and what types of things are vectors. So our next definition is position. And this is going to get a little technical here before I get the chance to explain. But position, the symbol for position is X. And a position is just where an object is located in space compared to a reference point. So that's the key here, that reference point. And usually that reference point, we make that point the origin. So if you think about where a point or an object is located compared to the origin. So that's position. Position is where something is compared to the origin. Our next definition is distance, which its symbol is d, lowercase d. And the distance, you might be kind of familiar with this, you might have an idea in your head of what distance is, but distance is the total ground covered by a moving object. So that ground covered is kind of just like how far something is going, no matter what direction it's moving in, just the total ground that's covered by a moving object over a certain period of time. Similarly, our next definition is kind of like distance, but it's different. It's called displacement. And the symbol for displacement is not d, because we already used that for distance. The symbol for displacement is delta x. So we've got another Greek letter there, that delta, that triangle. But the displacement tells us the change in position of an object. So that delta symbol represents the change. So the change in x, or the change in position, right? Position is x. So that's what displacement is. But you'll notice that the total ground covered and the change in position, they're kind of similar ideas. So they have the same units. They're units of distance or length. So this could be meters or miles or feet or centimeters or steps or whatever it is. They're units of length. The primary one that we use in physics is meters, though. So that's the same for distance or displacement. We measure it in meters. But the key difference between these ideas is that distance is a scalar. It doesn't matter which direction you're traveling in as long as you're covering ground in distance. But displacement is a vector. It does matter which direction you're going in because you're taking into account the change in position. And again, that change in position is represented by that delta x. Right, change in position, delta means change. So really what displacement is, it is your final position minus your initial position. So remember, if you're finding the change, you take the final minus the initial, and we're finding the change in position. So this is going to be a good equation for you to remember, and you be able to do it in your head most of the time instead of trying to write it out like that. But to kind of help facilitate our understanding of these ideas, I've got a little video again for us. What I have here is a setup. That second tree on the right or on the left there, I'm going to make my origin, my reference point. So if that is my reference point, my origin, I have an object, which is, yes, me in a T-Rex costume. That's me. I am going to change my position based on this reference point. So I'm walking away from the reference point. I take 8 steps and I stop. And there I am. So compared to my reference point, my position is 8 steps. That's my position. But obviously I can change that position based on where I am compared to the tree. So I can keep walking. I can take a few more steps there away from the tree to then be 8 steps further from where I started. So I started at the tree, so now my position is 16 steps. So that would be my position, 16 steps away from the tree. But what about distance and displacement? So let's go back to the origin, go back to the starting point. Distance and displacement, well, okay, let's say there I am again at my origin. Here's my origin, it's right where I start. And I'm going to start walking again. That's my initial position, is at the origin, 0 steps. I'm going to take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to take 12 steps and stop. And that is my next position. So right there, I'm at 12 steps. So my distance would be 12 steps. I took 12 steps. That's the total ground I covered. But my displacement is also 12 steps, and it's 12 steps to the right. But then I can travel back towards the tree. I can take 6 steps back towards the tree. Well, what's my distance and displacement now? My distance is from where I started, the total ground. So if I took 6 steps backwards, that means I'm located at 6 steps away from the tree. So my distance would be the total ground I covered on my 12-step journey out, and then 6-step journey in, which is 18 steps. So that's my total distance is 18 steps. But my displacement only matters where I started versus where I ended. So my displacement would be 6 steps to the right. 6 steps to the right of the origin. So that is kind of the difference between distance and displacement. I hope you enjoyed me in a T-Rex costume there. We'll be talking a lot more about distance and displacement as we continue on in this unit. But now we're going over to Mr. Willauer to talk to us about average speed and average velocity.
So Ms. Nielsen took you through very nicely some of the terms from this new unit: scalar, vector, distance, and displacement. I'm going to be taking it a step further and talking about 2 really important ideas, and these ideas actually have those other ideas included in them. The first one is average speed. Average speed. You should have this definition written down. Average speed is defined as the total distance traveled divided by the total time. If I were going to write this in an equation, it would look like this. S with a bar over the top, that stands for average speed. And that's going to equal, what do you hope we use for distance here? We use a lowercase d, so that's the total distance, divided by, and what are we going to use for time? We're going to use AT. So average speed is defined as the total distance traveled divided by the total time. The second term we want to talk about here is average velocity. So that's the next big one. Average velocity is defined as the total displacement traveled divided by the time, total time. So if I were writing that one down, this looks a little bit different here. Average velocity, again, it has a bar on top. That's my V. If you want to write a regular V, you can, but that's how I write a V for this one. So the average velocity equals, and then we have to put in the right term here. Where'd my pen go? Here it is. Total displacement. For that, we use delta x. That's the total displacement. That's the symbol we use, divided by, and time stays the same. So the big difference between average velocity and average speed: average velocity is the total displacement divided by time. Average speed is the total distance divided by time. So here we have average velocity on this side, average speed on this side. Here are the 2 relationships we had. What you calculated in your activity from Monday, Tuesday this week, you are actually determining your average speed, because all we asked you to do was figure out a route, a total distance, and divide it by a time. That'll give you your average speed. If we would have had you calculate your average velocity during that, well, if you start at home and you end at home, your displacement is 0, so your average velocity would be 0. So these are the 2 ideas here. 2 other things that I want to tie together here. And it's the units. The units for average speed and velocity are the same. They're a distance over a time unit. So units for velocity and speed might be meters per second, or we would have the one you're really familiar with, miles per hour, or we might have centimeters per second. So we've got different units we can have there. The final thing I want to point out here is comparing this with 2 other terms. Velocity is a scalar quantity. Sorry, said the wrong one. Velocity is a vector quantity. Ms. Nielsen defined that for you. A vector quantity is something that has a direction as well. Average speed, on the other hand, that is the scalar quantity. So the difference between those 2, a vector quantity, you have to give a direction with it. So you might be saying 40 miles per hour we'll say east. If I say that, I have given you an average velocity here because I give you the 40 miles per hour and I give you the direction. That would be a vector, which means we're talking about velocity here. If I said over here just 40 miles per hour, then that would be just scalar because there is no direction here.
Thanks, Mr. Willauer, for those awesome definitions. And thank you for joining us once again on Physics in Action. I hope you enjoyed learning the very important differences between position, distance, and displacement, as well as the vital distinction between speed and velocity. Until next time, I'm Miss Nielsen, Physics in Action.